Good morning, students. In the last class, we discussed about the variation of conductivity and molar conductivity with a concentration. So already you know that as conductivity of specific conductance increases as the dilution increases. Okay, as well as we have discussed about limiting molar conductivity. Okay, so that is for strong electrolyte, the limiting molar conductivity can be obtained by plotting the graph of molar conductivity versus root C. But if you go for weak electrolyte, the molar conductivity cannot be determined. That is the molar conductivity of root C. Okay, so therefore the Colorage next one is that is Color's law. He obtained the in order to determine the molar conductivity at infinite resolution for weak electrolytes. So already we know that molar conductivity of electrolyte, that is lambda m, it is increases. Okay, that is molar conductivity increases with increase in dilution. Okay, so already we have studied this one. Okay, so means at infinite dilution. Okay, for strong electrolyte, that is lambda m versus root C. Okay, so you can determine lambda m naught by extrapolating the graph. Okay, so that one is like this, that is lambda m versus root C. Okay, so whenever it approaches this unit value, so that this one is limiting molar conductivity, is applicable for strong electrolyte. It is applicable for strong electrolytes. Fine. But in case of a weak electrolyte, you can't determine the lambda m naught. So in order to determine that one, the Colorage law obtained an experimental result. So it is known as Colorage law of independent migration of ions. So it states that at infinite dilution, at infinite dilution, when dissociation is complete, each ion makes definite contribution towards molar conductivity. So that is nothing but so molar conductivity at infinite dilution, molar conductivity of an electrolyte at infinite dilution can be expressed as sum of the contributions from its individual ions. Okay, so this is the Colorage law statement. So means at infinite dilution, so almost the dissociation is completed. So on that time, so each ion makes, whether it is a positive or a negative ion, each ion makes a definite contributions to its molar conductivity. So usually if you consider, for example, if lambda m naught, that is lambda plus naught and lambda minus naught, so represents represents limiting molar conductivity, limiting molar conductivities, limiting molar conductivities, limiting molar conductivities of cation and anion respectively. So lambda m naught, that is molar conductivity at infinite dilution, is given by, this is plus lambda plus, then plus of lambda minus, this one is lambda minus. So this is not okay. So therefore, where these were plus and minus, nothing but number of ions present in the system, number of ions present in the system, number of ions present in the system. For example, so if we write for NaCl, so lambda m naught for NaCl is nothing but lambda naught Na plus, then lambda naught Cl minus. This is the first example. The second example, if you take for barium chloride, so lambda m naught for barium chloride, so this is nothing but lambda naught for Ba2 plus, then 2 into lambda naught for Cl minus, because there are two Cl minus ions present in the system. So if you go for next third example, for Na2SO4, same thing, lambda m naught for Na2SO4, so there are two sodium ions, so therefore it becomes lambda naught plus of Na, fine, then plus of, then only SO4, lambda SO4 2 minus. So this is nothing but, so whenever a particular electrolyte that will undergo dissociation, so means each ions, whether it may be a negative or a negative, whether it is a negative or a positive, each ion makes a definite contribution towards a molar conductivity. So this is based on Coleridge law, means at infinite dilution the molar conductivity of an electrolyte can be expressed as sum of the contributions from its individual ions. So these are the example for NaCl. So there are two ions, Na plus and Cl minus. It is sum of the contribution of Na plus as well as sum of the contributions of Cl minus. Similarly, if you go for barium chloride, so barium 2 plus, there are two chloride ions, therefore it is a definite, it is nothing but sum of the molar conductivity of barium plus 2 plus ions as well as two chloride ions present in the system. If you go for sodium sulfate, the same equation, here the two sodium ions will be present, so these two ions will make a definite contribution to the molar conductivity. Okay, so next I will go for, that is applications of Coleridge law. Applications of Coleridge law. So first one, calculation of limiting molar conductivity, that is lambda m naught of weak electrolytes. So already we have studied lambda m for strong electrolyte can be obtained by, that is a graph of lambda m over to by extrapolating to zero constant. But for weak electrolyte, this lambda m naught cannot be determined by this graph. So therefore it can be obtained with the help of, it can be obtained with the help of Coleridge law. It can be obtained with the help of this Coleridge law. Okay. So for example, like weak electrolyte, for example, for acetic acid. So lambda m naught for acetic acid. So lambda m naught for acetic acid. This is nothing according to Coleridge law. This one is definite contribution of acetate ions CS3CO minus, then definite contribution of H plus in this case. Okay, but this is obtained by this because it is a weak electrolyte. It cannot be obtained by lambda m versus root C graph, but it can be obtained. It can be obtained by considering the conductivities of that is strong electrolytes like a sodium acetate CS3COONA, okay, then HCl and NaCl. That is nothing but lambda, that is m naught for acetic acid, can be obtained by considering these strong electrolytes because these will undergo complete dissociation. So therefore it can be obtained by extrapolating the graph to the zero concentration. So therefore lambda naught for CS, for if you consider for sodium acetate, it can be written as acetate ion plus of lambda m naught Na plus. Okay, then again if you go for HCl, lambda naught HCl H plus and lambda naught for Cl minus. Then next one is you have to do the subtraction, that is lambda Na plus then minus of lambda naught Cl minus. Okay, so already you know this one. This one is a negative sign, this one is for both get cancelled. Here also Cl minus and Cl minus. The remaining term is lambda naught for CS3COH, that is molar conductivity at infinite dilution for acetic acid, nothing but. So this is lambda naught for, that is acetate ion, then lambda naught for H plus. Okay, so means here by considering the strong electrolytes, and once you know the values of molar conductivity and infinite dilution for strong electrodes, so you can get that is molar conductivity of a weak electrolyte infinite dilution. So this can be obtained by using this Coleridge law. Similarly you can determine for NH4OH, that is ammonium hydroxide, second weak electrolyte. So by considering by NH4Cl, okay, next one is NaOH, next Cl. So by considering these strong electrolytes, so you can determine that is molar conductivity at infinite dilution for ammonium hydroxide also. This one is the first example, means for the calculation of molar conductivity of a weak electrode. And second application is calculation of degree of dissociation. Calculation of degree of dissociation of weak electrode. Calculation of degree of dissociation of weak electrolytes. So already we know that for strong electrolyte degree of dissociation is more than 1 because they will undergo complete dissociation. Okay, but in case of a weak electrolyte the degree of dissociation is always less than 1. So therefore the degree of dissociation for weak electrolyte can be calculated by considering this Coleridge law. So that one already we know that at infinite dilution the concentration approaches to 0. Okay, So and degree of dissociation, the degree of dissociation, the degree of dissociation, degree of dissociation approaches unity. Degree of dissociation approaches unity. So this is according to, that is Ostwald dilution law. This is according to Ostwald's dilution law. It is based on Ostwald dilution law. So therefore, lambda m for, that is molar conductivity of electrolytes, becomes maximum. So at this stage, lambda m becomes maximum. Lambda m becomes maximum and attains limiting molar conductivity, limiting molar conductivity. So that is nothing but lambda m naught. Okay, so that is at infinite dilution means the concentration almost approaches to zero, because on that condition the degree of dissociation approaches to unity. This is based on Ostwald dilution law. Okay, at this stage what happens, the molar conductivity becomes maximum and attains some limiting molar conductivity. This is at zero concentration. So if lambda mc, that is the molar conductivity at any concentration, and lambda m naught is the limiting molar conductivity, limiting molar conductivity. So therefore the degree of dissociation is given by, then alpha is given by, then alpha, that is nothing but degree of dissociation is given by so degree of dissociation alpha is equal to, that is molar conductivity at any concentration divided by limiting molar conductivity. So based on this equation you can determine the degree of dissociation of a weak electrolyte. Okay, so this is the second applications of, that is Coleridge law. Third one is calculation of dissociation constant. Calculation of dissociation constant. That is K of weak electrolyte. Calculation of dissociation constant of weak electrolyte. Okay, so for binary electrolyte, like this is binary electrolyte, the dissociation constant, that is K, is related to dissociation constant is related to degree of dissociation, that is alpha as, that is K is equal to C into alpha square divided by 1 minus alpha. This is for a binary electron. But already we know that the degree of dissociation is nothing but this equation, that is molar conductivity at any concentration divided by limiting molar conductivity. So therefore K is equal to, that is C into lambda C lambda naught, that is molar conductivity square, 1 minus lambda mc divided by lambda m naught, or this can be written as C into lambda mc square divided by lambda m naught square, then lambda m naught, if you take LCM this one, lambda mc divided by lambda m naught here. Okay, so this lambda over lambda naught and 1 lambda naught get cancelled, so therefore the equation becomes C into lambda mc square divided by lambda m naught, that is limiting molar conductivity, into limiting molar conductivity minus molar conductivity at that is at any concentration. Based on this equation, you can determine the dissociation constant for a weak electrolyte. So this one is an equation is used to determine the dissociation constant of a weak electrolyte. So next one is determining the solubility, that is the fourth application, that is determining the solubility of sparingly soluble salts, sparingly soluble salts. This is the fourth and last application part of a colorimetry. So means already you know that ionic salts like that is silver chloride, okay, then silver chromate is to CrO4, then barium sulfate, okay, magnesium hydroxide and lead sulfate, etc. So dissolve in these components, dissolve in water to a very small extent, and called as saturated solution, or called as sparingly soluble salt, okay. So these components like silver chloride and silver chromate, barium sulfate, magnesium hydroxide and lead sulfate, these dissolve in water to a very small quantity or a small extent, and therefore these are called as sparingly soluble salts, and their aqueous solutions are called as saturated solutions. Hence the concentration of such salts in their aqueous solution pertains to their respective solubility, and it can be calculated it can be calculated by conductivity K and molar conductivity of an electrolyte, of an aqueous solution, of an aqueous solution, of an aqueous solution. So that is nothing but molar conductivity. Already we know the definition, 1000 into K divided by, that is molarity. Okay. So already you know that this molarity is nothing but a particular quantity of the salt or particular quantity of an electrolyte that is dissolved in a solution. But in case of sparingly soluble, only a part of it is soluble, that itself represents its concentration. Therefore, this can be written as 1000 into conductivity divided by solubility. Because here whatever the quantity it is dissolved, that itself represents its concentration, that is in turn is nothing but its molarity. Therefore, the lambda m naught determining the solubility of sparingly soluble salt. So therefore the solubility is given by, solubility is equal to, that is 1000 into conductivity divided by, that is molar conductivity and equivalent dilution. So this is the, based on this equation, so you can calculate the solubility. The unit for this one is mole per liter. So these are the different applications by using Coleridge. So this is specially applicable for a weak electrolyte. The first one is you can determine the you can calculate the molar conductivity of a weak electrolytes by considering the strong electrolytes. Second one is you can calculate the degree of dissociation of weak electrolyte by considering a molar conductivity at any concentration divided by the limiting molar conductivity, that will give you the degree of dissociation. And third one is, so we can calculate the dissociation constant of a weak electrolyte also. And last one is, this one is application, that was a determination of or determining the solubility of a sparingly soluble salts. So these are some of the examples for a sparingly soluble like silver chloride, silver chromate, barium sulfate and magnesium hydroxide. So these dissolve in a water to a very small extent. So therefore these are called as a sparingly soluble salt, and their solution is called as saturated solutions. So hence concentration of such solutions nothing but that is a solubility. Also whatever the quantity that is dissolved in aqueous solution, that itself indicates that its concentration. So therefore the molar conductivity, already we know the definition, molar conductivity and infinite dilution is equal to 1000 into, that is conductivity divided by molar. The molarity itself is nothing but its solubility, because only a part of it is soluble, it is in a aqueous solution. Therefore the solubility is equal to 1000 into that is conductivity divided by the limiting molar conductivity. So this can be expressed as mole per liter. So this is about Coleridge law.